talk to you and give this mini course here. The course is going to consist of 2 parts. Today I will be giving you a quick overview of the basic theory, so I will be talking about the main ingredients of large deviation theory and trying to give you a little bit of history, a little bit of examples and explain to you what is really driving the whole theory and why it's so important. And then tomorrow I will talk about one particular application, and this is what happens when you have a random sequence of letters and you draw randomly from these sequence pieces so that you generate random words. And I will be talking about large deviations for this problem, and this problem is very important because it is the key to 3 important phase transitions that we want to analyze for other types of systems. But let me get to that tomorrow and explain why that is important. So I'm going to start today with the basic theory, and I'd like to begin by saying what large deviations is. And of course many of you know this. It's a theory that tries to study unlikely events. And your first reaction might be, why are we at all interested in unlikely events? If they're unlikely, why should we bother by them? The point is that unlikely events are sometimes very important if you have to make a decision about how big a dike you want to build. In my country, if you don't want to be flooded in the next 500 years, you have to talk about very rare events. They're also important because if you have a system that is complicated because it has some interactions built in it, then very often you can only understand this well if you understand large deviations of a system without interaction. And so therefore large deviation is a major tool in statistical physics. In fact, large deviations in some sense started with statistical physics. So around 1900, with the theory of Boltzmann and Gibbs, there were things happening that later we recognized as being part of large deviation theory. Then in the early 20th century there was a lot of work coming from insurance mathematics and finance mathematics, and that's where large deviation theory also started to grow and become very prominent, and people recognized that there was a big connection with what people had been doing in statistical physics. And then finally it entered probability theory, and in the hands of Donsker and Varadan and other people like Lanford, it became a very versatile theory, and now you will find large deviations in almost any discipline. It's a huge area, very successful, and I think it's completely justified that Varadan got the Abel Prize for this beautiful work, because I think he should be considered the chief architect of the area. Okay, I'm going to, before I even start to become formal, I want to give an example that we all know very well, and this is a way for you to appreciate something. If we are given a sequence of i.i.d. r-valued random variables, so a very classical setting, and suppose I say that the expectation of x1 is mu, and this can be any number in R, and the variance of x1 is sigma squared, and it's a number between 0 and infinity. Then, and I introduce a quantity that I call x bar n. It is 1 over n times the sum of the first of these n variables. So this is what we call the empirical average of the n sample of the first n quantities, then we know that there's a very famous fact, the law of large numbers, that says that x bar n will converge to the number mu, this expectation, as n goes to infinity, p almost surely. And there is the famous central limit theorem that says if I take square root of n x bar n minus mu, then this will converge in distribution, and we use a different symbol for that, to sigma squared sigma times z, and this is in p law, so in p probability, where this thing here is a standard normal random variable. Right, so these are very basic facts from probability theory, having been used over and over and over again in many settings. And now, what is large deviations going to do? It is asking the question, what is the probability that this empirical mean is close to a certain number, let's say nu, where nu is not equal to mu. So this says, well, I'm converging to mu. This says I'm actually very close to mu, a distance of 1 square root of n. And saying, but what is the probability that I would not be close to mu? I would be close to another number different from mu. Then the large deviation theory will tell you that this would be minus n of I of nu plus something that is small compared to n, where this I is what is called a rate function. And this is again true for n going to infinity, and this rate function should typically be looking something like this. Okay, and I'm being vague here. This picture might look a bit different, but sort of the paradigm idea would be that this is what is happening. And so large deviation theory tries to go beyond these two basic laws by saying we want to know what the probability is that you're really very different from your mean. And the statement is you will be exponentially unlikely to be close to your to be away from that mean, and how much is quantified in an exponent that depends on where you want to be in the neighborhood. And this kind of result, this would be called a large deviation principle, and this is an old result due to Cramer already in the 30s and 40s, and this is an example in this big theory of large deviation theory that I'm going to tell you about. So it's good to realize what in this very classical setting what it is that we're talking about. Okay, and you can generalize this to sequences that are not i.i.d. If they have some nice structure, there could be a Markov sequence, or they could have some nice mixing properties. Then you can all work your way through and prove law of large numbers, central limit theorems, large deviation principles, etc., etc. But this is the kind of simplest example in a big theory that deals with such questions. Okay, now what I'm going to do is to immediately jump to the formal setup as large deviations builds it up. So you could say, well, let's go and go deeper into these cases, but sooner or later you will find out that all the cases of large deviations have a kind of common structure, and it is due to Varadan. He stated the format in which large deviation theory should be built up. And it begins by giving a definition, and this definition is called the large deviation principle. By the way, so Siva, at the end of next week you will put all the slides on your homepage, so all the talks will be available, and after I've talked about this I'm going to make some further changes depending, so this is still in the process, but it will all become available. Okay, so
and the talk will be recorded.
Yeah, okay. Now, the large deviation principle is a statement that applies to a sequence of probability distributions. And the probability distributions could, for instance, be the probability distribution of this random variable, or it could be the probability distribution of any other random variable that I might think of. So, in complete generality, you are given some sequence of probability distributions. Now, I use a parameter epsilon, but in many applications, actually, this epsilon would be something like 1 over n. And that you would therefore have here a sequence of probability measures that depend on a parameter n, like it is here. Here, the n was a natural thing to use because we were labeling your variables by n, but we could do the labeling with any other parameter. If you, for instance, would want to do things in continuous time, you would need a continuous parameter. So this epsilon can represent anything in the model that you want to look at. So no problem to think of it in this generality. And we want to state the large deviation principle when we have probability measures living on some Polish space. I'll say later something about more general spaces. So you say that the sequence of probability measures on this Polish space X satisfies a large deviation principle with a certain rate function, which would be a function living on this Polish space, if three things happen. First of all, you want this rate function not to be identically equal to infinity, because if that would be the case, you would have been looking at the wrong scaling limit. You want it to have compact level sets, so this means that the set where this rate function is smaller than or equal to some finite value has to be a compact set. And then there is a lower bound for these probability measures on open sets, and that's very important. If you take the lim in for epsilon going to 0, this probability is supposed to go to 0, so so this will become very big, and you have to multiply it by epsilon to get a limit. And you have it here that for any open set it has to be below something which is just the infimum over your rate function over the set in which you are looking here, and this would be open sets. And for closed sets you need an upper bound saying the lim sup of the same thing on a closed set would be bounded from above by minus IC, and IC would be the infimum over all x in the set C of this rate function. And if this is true for all open sets and all closed sets, then we say that we satisfy the large deviation principle. So the large deviation principle is a property which you can assign to a family of probability measures. Now, if you've never seen this before, you might say, why these inequalities? Isn't it what you really want is that the limit of epsilon going to 0 of epsilon log, where epsilon is going to some set? Why don't you do that? Well, that's too stringent. It's like if you have convergence of probability measures in the weak topology, you don't want to require this for every set. It's enough to get upper and lower bounds for open and closed sets, and that's the way to formulate it. So you could think of the LDP as a kind of exponential version of the notion of weak convergence, right? This compact level sets is important, and some people say when you have this, you have a strong LDP. And informally, what this says is the following. You should read the result as saying, if I take a point x, and I take a very small ball around this point x, so think of d as being a very small number, and I look at the total weight that I get for this little neighborhood of the point x, then that weight is e to the minus ix over epsilon. And here is something that is sort of negligible, converging to 1. When epsilon gets small, and you have to do this for every positive delta, for every some positive d, and you let d go to 0. So this is sort of saying, what does the measure locally look like? And it says locally it has an exponential structure that can be approximated by this rate function. So that's the kind of way you have to think about it, and you have to talk about little balls because you know, you cannot always talk about the Lebesgue measure. Right. And typically your rate function would look something like this. It would have some 0, and typically it would have this shape. Now, this picture is again a gross simplification, because it could be that this rate function could become infinite somewhere. It could have, you know, there could be more than 1 0. So many things are possible, but very often, and certainly in that very classical situation that I mentioned before, the rate function always looks something like that. And the minimum is supposed to remind you of the law of large numbers, and somehow the curvature here near the minimum is supposed to remind you of the central limit theorem, and this is the kind of paradigm picture. Okay, now I want to do one nice thing immediately, and that is to show to you that if you have a large deviation principle, your rate function must be unique. It cannot be that you have a family of probability measures and it satisfies the large deviation principle for 2 different rate functions. And there's a very simple argument to prove that. So here's the proof that I is unique. So what you do is you go by contradiction. You say, suppose I and j are both rate functions in the LDP of some one and the same family of probability measures. Then you would say, pick any point in your Polish space and consider a sequence of balls which are defined as the open ball of radius 1 over n around the point x. So I pick a point x here, I have my big space, and I'm thinking of concentric balls converging to this point, shrinking around this point x. And then I do the following reason. I say minus ix is less than or equal to minus I of bn plus 1. Why? Because this is the infimum over this function over this ball, and since this ball contains the point x, the infimum is lower than ix itself, and so minus, it can only go up. Okay, and then I say, now this is an open set, so I can use the lower bound in my large deviation principle. So the lim inf of epsilon going to 0 of epsilon log mu of epsilon of this ball is certainly greater than or equal to minus I. And then I say, well, but that thing is certainly bigger than the lim sup of this thing here, but I'm going to make it even bigger by closing this ball. So by adding the boundary of the ball, so it's already bigger because of the lim goes to the lim sub, but I'm also closing it. Now, because I have a closed set, I can use the large deviation principle upper bound and say that this is bounded from above by the j minus the j of the closure of this ball n plus 1. Right? And now I'm using the large deviation upper bound for rate function j, where I've been using the large deviation lower bound for I, and I can do that because they're both rate functions in the same LDP. And then I claim that this is less than minus j of, I can remove the closure because I go from n plus 1 to n, so I go even up. And now I'm noting that the limit of n going to infinity of j of bn is j of x, because j is lower semi-continuous. In fact, it has compact level sets, so it's lower semi-continuous. And a lower semi-continuous function has a property that if you take the infimum over a shrinking set, you will get the value at the point itself. So the net result is that minus ix is less than or equal to minus jx, so I of x is larger than j of x. Okay, and now I'm done because I could reverse the roles of I and j, and I get equality. And this was true for any choice of x, so I've proved equality. Okay, so this is a very simple computation where you see how that these two inequalities that you put in your large deviation principle are the right thing to have in order to prove a simple fact like rate functions must be unique. Okay. Now, if the level sets of I are not compact, then not everything is lost. Sometimes, there are versions of the large deviation principle which are called weak large deviation principle, where you require your upper bound to be true only for closed sets and not for compact sets. Okay, so there are various versions of this that you can play with. The most common version is the version that I wrote down, and they are linked in some way. If you have a large deviation principle, then your family of probability measures must be what is called exponentially tight. So it must be that uniformly in epsilon, the probability that you are charging something outside a compact set is getting very, very small. So this is a strong way of saying that the mass cannot flow away to infinity, and it cannot do that even on an exponential scale. So when you have an LDP, you have this property, and when you have some softer form, this property suffices to get the strong form of the large deviation principle. Okay, so this is the kind of general setup, and this sequence of probability measures mu epsilon could be anything you like. They could be, epsilon could be 1 over n, and then this could be a probability measure of the sum of some random variables or the sum of some dependent random variables. In principle, this allows you to to put many concrete examples into this kind of framework. Okay. Now, the large deviation principle is a definition. It's a property that you assign to a sequence of probability measures, and it has a lot of consequences. So I'm now going to talk about what can you do with this large deviation principle. Okay, and the most important result in here is Varadan's lemma, and it says if you have an LDP, then you have very good control over exponential functionals, exponential integrals of your probability measure. So it says the following: suppose you have a family of probability measures satisfying an LDP with a certain rate function, and suppose you are interested in an integral like this. You are given some function and you'd like to integrate this exponential e to the fx divided by epsilon over your probability measure, and you would say, well, what are such integrals doing? How do they behave? And the statement would be, if you take the logarithm of this integral and multiply by epsilon, then you would get a number. And you would get a number for any f that you might want to pick, provided it is bounded and continuous. And the answer would be, take the function that you are interested in, subtract the rate function, and take the supremum of the difference. So Varadan's lemma is in a sense nothing other than Laplace's principle of integrals using steepest descent, except this is put into the right general framework, and it's the right general formulation of this principle. And I want to again give you a kind of quick feeling behind this. The proof of Varadan's lemma is not complicated, but I'm going to give you a heuristic explanation, and the heuristic explanation is very much in the spirit of Laplace principle. You say, well, what is this integral that we are interested in? Okay, well, I'm going to, my large deviation principle has told me that this is sort of like e to the minus I of x over epsilon times dx. That's what the large deviation principle is saying. Now you might say, well, what is this? Would this be a Lebesgue measure? So I actually want to put sort of quotation marks around this. So I want you to think of this as a kind of a small neighborhood of the point x, so in order to be precise. And so suppose that if I would substitute this, I would end up with this integral, and by Laplace's principle, this should be e to the supremum over all x of f of x minus I of x, and that whole thing divided by epsilon, because this integral will be almost entirely carried by the little region where this assumes its supremum. So this is basically the Laplace principle. And so this is exactly then what Varadan's lemma is saying, that such integrals grow exponentially with this supremum. And formally this is not correct, because this does not exist. I should think of this as a small neighborhood of the thing. You have to be here special about what that means. You have and what does this mean, and what does that exactly mean? And Varadan's lemma is just making that all precise. Basically, what you do is you cover your space X with a number of small balls, and you slice your space also according to let's say slices where the f doesn't change so very much, it's almost constant, and then you can do appropriate approximations, and in the end you end up exactly with this formula. So the formal proof to make that heuristics precise is not difficult, and you can find it in any book on large deviations. That is the way you have to memorize why Varadan's lemma is true. Okay, and this lemma can easily be extended to functions that would not be continuous or not bounded. If f is sort of decent and you have some control over the tail properties of your family of mu epsilon, there are many examples where you can include this for even more general functions. And this is also not very difficult, and it's important because we want to apply Varadan's lemma to lots of cases where the function is not so nice, but this can be done. Okay, so Varadan's lemma is the first result where you say, that's nice, if you have an LDP you can get a hold of all sorts of asymptotics of exponential functionals. And this idea is very important in statistical physics, because in statistical physics you look at systems where there is some interaction, and you say, well, what would the system do if there would be no interaction? And that would be described by some nice simple family of probability measures, and of which you have good control, in which you could hopefully prove some LDP. And then you say, the moment I switch on an interaction, there will be something that biases the probability distribution according to what we call the Gibbs factor, the Boltzmann factor, and then the combination of these two is really describing the system with interaction, and therefore such integrals are constantly popping up in statistical physics all over the place, and the fact that you can control such integrals for very general functions would mean that you have good control of the behavior of systems for very general types of interactions. So this thing here, which for us here looks completely like a probabilistic statement, is key in many applications where you want to look at more complicated systems with interactions, and it is the f that carries those interactions. Okay, now that in itself would be a whole course on statistical mechanics, which I'm not going to get into. We think of it cleanly in the world of probability theory. Okay, now there is an interesting inverse of Varadan's lemma, which is due to Walter Bryc, and it says, Varadan's lemma says, if you have an LDP, then for all bounded continuous functions I know what exponential integrals are doing. Bryc's lemma goes the other way around. It says, if I know what all exponential integrals of bounded continuous functions are doing, then I must conclude that there is a large deviation principle in the background. And that is what it is saying. It says, if I have any family of probability measures that is exponentially tight, not knowing yet that they would satisfy a large deviation principle, and I would know that the limit in Varadan's lemma would exist, not knowing what it is, then I can retrace what the underlying rate function is by basically inverting the variational formula that was in Varadan's formula. So it is basically, you say, you now know all such integrals, so you know for every f you know this, so then you just are supposed to take f minus all these values and take the supremum over all bounded continuous functions, and you would find back your rate function. So the rate functions and the exponential integrals are intimately linked in a one-to-one fashion, right? And you do not need to know this for every bounded continuous function. You can take a dense set of functions for which this is true, and then you would be able to do it. So Bryc's lemma is sometimes referred to as the inverse of Varadan's lemma, and it is a nice property, and sometimes you can prove an LDP through Bryc's lemma. Okay, so now once you have an LDP, you can very often create other LDPs out of it. So suppose you have a nice measure where you have an LDP, then there are ways of saying, but then there are also other measures for which you have a large deviation principle. And I'm going to give you 3 examples through which you could do that. And they're all 3 very important and very useful. And I refer to them as forward principles because they are a way of generating one LDP out of another. Okay. Now the most simple one is a forward principle which has its own name. It's called the contraction principle, and it is saying the following: suppose you have a sequence of probability measures satisfying an LDP on a Polish space with a rate function y, and suppose that there is some other second Polish space and a map, a continuous map from my original Polish space to my new Polish space, and I apply this map to my probability measure here. So I'm saying what is the image, if I have a mu here, what is the image under t of the measure nu? So I'm thinking of this picture here. I'm having a Polish space here and a probability distribution on this Polish space, and I have a map to another Polish space, and you could say the measure here gets mapped onto a new measure on the image Polish space, and that would be given by nu. And I could do this for every epsilon, so I didn't put the epsilon under here, but in principle you should have this for every epsilon. Then what the contraction principle says is that this new family of probability measure on the new Polish space again satisfies a large deviation principle, and it has its own rate function, and the rate function is just obtained from the original rate function by taking the infimum of that rate function over all points that get mapped onto a point y at which I want to consider the new rate function. Right? And that is what, so how you get a new LDP out of an old LDP. Okay, and I'm going to give you a sketch of why this is true. And again, I'm going to be, I can be quite rigorous this time. If t is continuous, then that implies that the inverse of t maps open sets to open sets, and it maps closed sets to closed sets. So by the continuity of the map, the open and the closedness are not getting lost. So now I would say pick a set that would be a closed set in your image Polish space and do the following. What is the lim sup of epsilon log nu epsilon of c? So I'm trying to see whether this measure satisfies some large deviation principle. So I say let's look at the lim sup. This should satisfy the upper bound in the large deviation principle. So what is that? I say, well, this is also the lim sup of epsilon going to 0 of epsilon log mu epsilon of the inverse of t applied to c. That's just recalling what the definition of nu epsilon is. Then, because the mu satisfies the large deviation principle upper bound, this becomes minus I of the inverse image of the C, because mu satisfies that. Now, because of that definition of Jy, I can say, but this is equal to minus the infimum of x over t minus 1 of c of Jy. Right, I'm just, if I substitute that definition of J in here, I see that this is literally equal to that. Right? And now I just have to say, sorry, I made a mistake. This should be C. Sorry for that. Yeah. And then I say, but that's by definition J of C. So the large deviation upper bound holds with J being equal to this formula. Okay. And I can do the same sort of argument playing with an open set, and I get the large deviation bound for the open set. So I would have found that with this formula for J, I satisfy my large deviation principle. And since I already know that any large deviation principle can have only one rate function, this must be the unique rate function of the image measure. So I verified for this one, and I know that this then must be the only one. So again, you see how I can manipulate these inequalities that are in the large deviation principle to prove this principle. Right. And so here you see an important example. If you have an LDP, then with any continuous map, you can actually get other LDPs. And then once you have those LDPs, you could apply Varadan's lemma to those, with those LDPs, and you begin to start to get more and more results as a result. So this is a very important principle to work with. Okay. Here's another forward principle. And this is called exponential tilting, also very important. Suppose you are given, again, a family that satisfies an LDP, and I'm tilting this with an exponential functional, and I'm normalizing this measure so that this is also a probability measure, and for that the normalization constant is exactly the integral as we've seen it in Varadan's lemma. Then I get a new family of probability measures, and the statement is this probability, this family also satisfies an LDP with its own rate function J, and J is nothing other than the supremum of this difference as we've seen it in Varadan's lemma minus the difference itself. Okay, and again here the argument is very simple. Why is this the case? And I'm going to be again very informal. What should this measure be? Well, I have just said that this is defined as e to the fx divided by epsilon, and then there's mu dx, but the mu dx was sort of e to the minus I of x over epsilon dx, where again I put the quotation marks because I want you to think of d of x as a very small neighborhood around x. And so what have I then standing here, I see that this is nothing but e to the fx minus ix over epsilon dx. And this thing here, we know by Varadan's lemma. So Varadan's lemma, that this would be e to the supremum over all x of f of x minus I of x divided by epsilon, because Varadan's lemma tells me how fast this grows. And then basically this is then exactly telling me what I see here is e to the minus j of x over epsilon dx. Okay, so again, if I do some very simple hand waving argument, then that's what it is. Yeah. Okay, so this is also important because you can modify a probability measure by some exponential factor and still stay having an LDP. And if I would go back to the world of statistical physics, it would mean, suppose I change the interaction a little bit. If I have a nice system and I perturb the interaction a little bit, I can still have a nice system. So that's why this is important. And the last thing I want to mention before we're going to have a break is the Dawson-Gartner projective limit LDP, which is also of immense importance. This is another way of interpreting, of getting an LDP as a kind of limit. So this says the following. Suppose I have a family of probability measures on some Polish space. I don't know yet that it would satisfy an LDP. And suppose I can subject this Polish space to a nested family of projections. So, and I would apply, I could label my projections by an integer n, and this would be, for instance, saying you could have some value, you could just say xn could be anything that is below the value n or above the value minus n. And I want this to be nested in the sense that as n goes to infinity, the projection essentially produces the whole space. So I want that the union of all the projections is just no projection at all. And I want this to be nested so that every projection so that they're ordered. And I'm going to transform my measure with all these projections, and I'm going to get projected measures. Okay, and the theorem says if I know that for every value of n, this projected family satisfies an LDP on the projected space with some rate function that depends on the projection label, then the original process out of which you have gotten these projections must satisfy an LDP, and the LDP is just what you get by taking a point in x, looking at the projection of this point x, looking at the value of the rate function for this finite n at that point, and then taking the supremum over all n's. And so it says if you are able to prove that a whole nested family of projected measures satisfies an LDP for every choice of the projection, then the original family must satisfy also an LDP with its own rate function that is obtained as a supremum. And in fact, you can see that immediately that the projected rate functions must come out of the LDP, out of the rate function for the full sequence in this way, and from this you see that actually this supremum is monotone in n. So if I increase n, this number is going to go up for every x. So this supremum actually has a limit. You can also say that you can take the limit of n going to infinity. And this is of immense importance because it allows you to obtain versions of the LDP in an infinite dimensional setting by proving things in a finite dimensional setting. So for instance, if you can prove an LDP for probability measures that live on the numbers 1 up to n, and you can do this for any n, and sometimes you can do this by calculating, and because you have a finite state space, you can do nice counting. If you find that that's true, then all you have to do is to let n go to infinity, and you would automatically get a large deviation principle for random variables that live on all of the integers. I could similarly go to the left, and I would end up with a large deviation principle on all of the integers. I could shrink the intervals between the integers, and I would end up with a large deviation principle on the real line. They are all consequences of taking a projective limit of simpler LDPs for which I can often prove something. So if I can prove something for anything that would live on a finite number of integers, and then I can very often get it in R, and then I can even get it in RD by looking at another projective limit going into different dimensions, etc. You can even go to more general things where you go to spaces of probability measures that you can approximate by some finite grid. And so this general fact immediately allows you to obtain an LDP in a very general setting from just knowing what it is doing in very simple settings and taking projective limits. And that is the best way in which you can prove that you have an LDP. And that is sort of the third and important principle through which we now know that it suffices to start with something simple. Out of this you can get a whole range of LDPs, and Varadan's lemma will tell you that for each of these LDPs you can control all sorts of exponential integrals. So this is becoming a rich and powerful theory to actually deal with. Okay, so let's have a break here.
There should be tea outside.
Yep.
Maybe 10 minutes.
We've been talking about LDPs on a Polish space. You can be more general. You can formulate LDPs on arbitrary topological spaces. This usually comes with a bit more technicalities, but in principle you can deal with that. Conversely, if you have much more structure, you can also get much more specific properties of your rate function out. So when I was talking about a Polish space, it could be completely general, but suppose I would be having a vector space, and that would not only be okay, then what happens that the rate function then can be obtained as the Legendre transform of some cumulating generating function, and I'm going to show that to you now. So I'm going to look at the case where my space is just the d-dimensional Euclidean space with the usual Euclidean metric. This becomes a Polish space, and I'm going to give you an example of a very direct way of computing the rate function in such a setting, and this is referred to as the Gartner-Ellis theorem. It was first stated by Jürgen Gärtner from Berlin, and later Ellis generalized this to a somewhat more general setup. So suppose I have a family of probability measures living on this d-dimensional Euclidean space where dimension can be any finite number. And suppose I build this integral, I integrate my probability measure against e to the u comma x inner product u of x, where this is just the standard inner product on Rd, and so u is some vector in Rd as well. And suppose I'm able to compute this limit. Suppose that that limit exists. That's an assumption in the theorem for every choice of u in Rd. And suppose that this function is differentiable on Rd. So that's the second assumption. If that is true, so if this limit exists and it's differentiable, then this family satisfies an LDP with a rate function. The rate function, I could have called it I of x. I'm giving it now a name phi of star of x for a reason that will become clear in a second. And this is just obtained by taking this function, subtracting it from the inner product of u comma x, and taking the supremum over x. So this thing here is the Legendre transform of this limiting function. And the Gartner-Ellis theorem says if these two conditions are true, then this is my rate function. And I'm using the symbol phi star now because this is a very particular and famous map going from phi to phi star, which is the Legendre transform, and therefore this rate function now deserves its own name. Right. And this is a wonderful and important theorem because you just have to get these two properties. There is nothing else that you have to do. You may not be able to compute such integrals, but if you can prove that they exist and they are differentiable, you have in principle a large deviation principle, and you have a formula for the rate function, which you can then try to study by trying to collect as much information as possible from this integral here. And if you're lucky, you can compute it, and if you're not lucky, you can estimate it, and you're in business of having an LDP and getting some information about your rate function. So this is a very powerful principle. This measure could be, again, anything. It could be describing the probability distribution of the empirical mean of a bunch of random variables that need not be independent. There is nothing requiring that this thing has a specific structure. So you can apply this theorem to any probability distribution of any random variable that you like, as long as you're able to control such objects in the limit. You are in perfectly nice situation. So, and out of this theorem, by looking at special cases of these measures mu epsilon, you can get many other famous theorems, and I'm going to, that have been around in the literature even before the Gartner-Ellis theorem, and I will talk about that in a second. You can even use this theorem to study large deviations of Markov processes, of many other processes, Gaussian processes. It's a very powerful tool. What is also noticeable is that this object is automatically a convex function on Rd. I'm not saying it's strictly convex, but it's convex. And in general, rate functions need not be convex. Of course, in vector space, first of all, you need to be in a vector space to be able to talk about the notion of convex space, but rate functions need not be convex. They often are, but in this particular case, they really are, and it has to do with this particular assumption, which is somewhat strong. This differentiability condition is very strong. If this differentiability condition fails, not everything is lost. You can still get an LDP, but you may have to do some extra work to get the LDP out. And it is also the case if this rate function, for instance, becomes infinity at some values of u. Also, not everything is lost, so I'm writing down the most simple version where this exists everywhere, and if it doesn't exist everywhere, so you can very often still do something, and there's no problem. So it's possible that this could be infinity somewhere, or this could be infinity somewhere. That's not a problem. We know how to deal with it. Okay, now I just mentioned that there are two famous, very classical and old theorems in large deviation theory, which is Cramer's theorem and Sanov's theorem, and I'm going to formulate them for you in a second. And they are much older. Cramer's theorem is from the 30s, and Sanov's theorem is of the 50s. And you can derive them separately by hand, but they actually also follow from the Gartner-Ellis theorem as a kind of corollary. And I'm going to state them for you now. They are looking at the very simple situation where, again, I'm giving an i.i.d. sequence of r-valued random variables. So this was the kind of setup I started with at the very beginning of the first hour. And suppose I know that these random variables have probability distribution rho on R. So I'm starting with a bunch of random variables that have that, and I want to study the large deviations of this sequence. And I will be looking at two quantities, the empirical mean and also the empirical distribution. And the empirical distribution will be living in a space of probability distributions on R, which we are supposed to view as a subset of the vector space of signed measures on R to realize in what vector space we actually are. And Cramer's theorem is the following. Cramer's theorem says if I take the empirical average, which is the quantity I looked at before, so I take the n sample up and find the empirical average, and let mu n denote the probability distribution of this object. Then I claim that the family mu n, where n is running over the positive integers, is satisfying in LDP on R with rate epsilon 1 over n. And it has the following rate function. What you have to do is to compute the moment, the lambda moments of the distribution of each of the single x's, which is rho. And this will give you a function m of lambda for every lambda. And we are assuming here that this integral is finite for any choice of r that you take. And by the way, I'm doing this Cramer's theorem now in one dimension. I could also do it in higher dimension, but that does not matter. I think you have to put in, you have to do in something. You're in the fortunate situation that this function is finite for every choice of lambda, then you can find the rate function that is describing the large deviations of this object as the Legendre transform of the logarithm of this function here, which we call the cumulant generating function of this measure rho. And if this is finite, then this is all well defined, and here is, you see that your rate function is again the Legendre transform of something, and this immediately follows out of Gartner's theorem, because now this whole integral becomes so easy. It becomes a product of similar integrals. This basically becomes this is just the moment generating function where u is equal to lambda. So it's a simple calculation. And it's sort of interesting to use this formula to see what this would give for your rate function. I'm going to look at three cases. So the first case is the standard normal distribution. So this would correspond to rho of dx being 1 over square root of 2 pi e to the minus 1/2 x squared dx, where x is in R. If I then do my calculation, I would find that m lambda would be e to the 1/2 lambda squared. So if you just stick this in and you complete the square, you will find that you have this, and your rate function would become 1/2 of x squared. So this looks here, the rate function is a perfect parabola. This is the standard normal case. So a very easy calculation. Second example is the Bernoulli distribution. So then rho would be 1/2 delta of -1 plus 1/2 delta of +1. So this is when the random variables have probability 1/2 to be -1 and 1/2 to be +1. And then you will find that the moment generating function is the cosine hyperbolic of lambda. And if you substitute that in that formula and perform the supremum, you will find that it's a slight calculation. You will find that this will become 1/2 1 plus x log 1 plus x plus 1/2 1 minus x log of 1 minus x, and this is the formula for x in the interval -1 to +1, and it is 0 if x is not in that interval. And here there is a picture that you find that the rate function sort of looks like this, and then it becomes plus infinity outside that interval.
Infinity, not 0, right?
Infinity, yeah, thank you. And this value here happens to be log 2. Okay, and then the third example, I need to move a little bit to the left because I've used up space here, is when you have a Poisson distribution with mean m, where m could be some positive finite number. In that case, rho of k is e to the minus m to the power k over k factorial for all k in n0. N0 is all the integers including the point 0. If you then do your computation, you will find that m lambda will be the exponential of m e to the lambda minus 1. So it's the exponential of something that also has an exponential in it. And if you do your calculation for the ix, you will find that this is x log x divided by m minus x minus m, and this is true for every x positive, and it would be infinity if x is not in that interval. And then the picture sort of looks like this. So it hits the value m and then sort of shoots up a bit faster than linear. Let's see, the value here is m, right? Because if I take x is equal to 0, this will go to 0, and this will be plus m. Yeah. So in all cases you see that there is unique 0. Here the unique 0 is equal to the mean of this, which is 0. Here the mean is also 0. Here the mean is m. So in all these cases you have convex rate functions that can become infinity outside a certain range and that have unique zeros. And they all follow from this formula directly. And you can pick your favorite probability distribution and find what your rate function is. Okay, so this is when you are interested in the empirical average of your random variables. There is another version of large deviations where you would be looking at the empirical distribution of your random variables. So what you now do is you look at all your first n variables, you put mass 1 at the value of this random variable. This is a probability distribution that puts all its mass on the point xi. Then you end up all these probability measures and you divide by n. Then you get again a probability measure. So this object, which is random because it depends on the outcome of all my random variables, but it looks at their empirical distribution. This is an element not of R, but of the probability distributions on R. And this is not measuring their average, it's measuring how they are sort of distributed over the line. And there is a theorem due to Sanov applying to the same setting that Cramer's theorem applies to, where you say this random variable, suppose I let mu n denote the probability now of this random variable, then this satisfies a large deviation not on the real line, but on the probability distributions on the real line, again with the same rate, epsilon is 1 over n. And the rate function is given by something that we call relative entropy. It's the relative entropy, so you're asking what is the probability that this object, which is a probability measure, is not close to the measure rho. There's, by Kolmogorov's theorem, we know that Ln will converge for large n to this measure rho of my random variables. So if I sample many of these random variables and I look at their empirical distribution, I find that this is very close to rho. And I'm now asking, what is the probability that you are not close to your typical value? Suppose that you are close to another probability measure nu, which is different from rho. Then the statement is the probability that that's occurring is e to the minus n I of nu, and this I of nu is the relative entropy of nu with respect to rho, and this is this integral here, where you're integrating nu against the logarithm of the Radon-Nikodym derivative of nu with respect to rho, with the proviso that if the Radon-Nikodym derivative shouldn't exist somewhere, then this will automatically become infinity. So, and this quantity here is a quantity that plays an important role in information theory. Relative entropy is a key object. You can think of relative entropy as some kind of measure of the distance between two probability distributions. If you have a probability distribution rho and a probability distribution nu, then h of nu rho is some kind of pseudo distance between nu and rho. There are many other distances that you could have, Wasserstein distance for instance, but in Sanov's theorem it's the relative entropy distance that actually then plays the role of the rate function for the empirical distribution. Okay, and I want to give you a little sketch of where this relative entropy comes from. I'm not going to do the full computation, but I'm going to give you again an idea of how you can get this by doing or let's say how you could guess this by doing a simple calculation, and I'm sure that this is what Sanov actually did. Actually, Sanov only wrote one paper in probability theory because he's a logician and a topologist, and we don't know much about him. There's only one picture on the internet, and he's a very enigmatic guy, but he wrote one paper in probability theory, and that was very important. So let's take the special case where rho has support on a finite set, where r is some integer. So a very simple-minded probability measure that has a finite support. Let's see if we could deal with that. Okay, then what I'm going to do is I'm going to define a set K of n. This is the set of all n vectors, k1 up to kn, and I abbreviate it by k. I'm not putting in, little r, such that, and this should be an element of n0 to the power r, such that the sum of all the ks's is equal to n. And so this is just a bunch of vectors in the r-dimensional lattice that sum up to n. And I want you to note that 1 over kn, 1 over n kn, is certainly a subset of the probability distributions on r to the power r, right? Because of this condition here. Now, an important fact is if the probability that this empirical measure at the point S is equal to Ks over n for all S in 1 up to r. That is very easy to compute. That is a multinomial. It's n factorial. Product of S is 1 up to r. Rho of S to the power Ks over Ks factorial. And that is very simple because this, if you want that for all the choices of S in R, this weight given by the empirical distribution to S is exactly equal to this number, you must have precisely Ks entries xi that produce the value S, and then you divide by n here because of this. So this sum will count, if you apply to the point S, how many x's are having the value S, and that is ks1. Every single one has a probability rho S. This is a multinomial factor that does the counting. And then we can finish the proof very quickly. I'm now going to define the Qn nu of delta as the maximum over all k in Kn of such that of this right-hand side, so let's call this here star, of this, the maximum of this star function over all k such that k over n is in the delta ball around nu. Right, so I'm going to give this as a definition. So this here is an analytic expression, and I say take this maximum of this expression over all points in this set such that k over n falls into a little ball around that measure nu that I would be interested in. So here I'm having my probability distribution on R. Here would be my rho. Here I would take another point that I want to be close to, and I would draw a little ball around it. I'm asking what is the I would be interested in knowing what the probability is that I'm in the neighborhood of this ball. And with this definition, there's a very important fact which says that this number, and this is defined for every nu in this measure and every delta positive, this is less than the probability that ln would be in that ball, and it's less than the cardinality of my set kn times qn nu delta. So
I think maybe 1 over n kn is a m1 of r, not m1 r die. Second line, a third line.
Yeah, this should be. Yeah, I'm sorry. Yeah, definitely. Yeah. So now this says the quantity that for Sanov's theorem I would be interested in, namely estimating the probability that I'm close to a measure nu that is different from rho. I have now bounded it up to a combinatorial factor by above and below by this analytic expression. Now this factor is at most of order n to the r. So if I take a logarithm, this is completely irrelevant, and I therefore only need to understand what the logarithm of this thing is doing. So basically the key object that I need to understand, so key object to understand is the limit of n going to infinity of 1 over n log q n nu. And then I would afterwards also like to take delta going to 0, so that indeed I will be very close in the neighborhood of this. Now, this quantity is very easy to compute because I have a formula here completely explicitly for this thing, and I'm only supposed to take an expectation and a maximum, and sort of what happens is that this thing is going to turn out to be, if you do the computation, to be roughly this nu rho plus an error that tends to 0 as n goes to infinity and delta goes to 0. So that's a very simple computation. If you put this in, you use Stirling and you use monotonicity properties in Stirling's formula. You see simply out of this formula that the relative entropy appears. So with a little bit of fiddling, you find that this relative entropy is simply appearing in front of your nose. And to make this into a precise proof is, again, you have to do some approximations, and in fact you're using that kn over n becomes a very dense grid in your space of probability measures. So, and you need that this function is actually continuous, except at the boundaries. So there is a little work to be done, and then you can look this up in the literature. But this is the calculation. This is the trick where you find a maximum and then you sandwich things between the maximum and the cardinality times the maximum. The cardinality here is not very harmful because I'm having a finite set. And once I have a finite set, then I can start to take a projective limit. I can now use Dawson Gartner projective limit to say, well, what can I do if rho is living on all of the integers, and what can I do when r lives on the real numbers, etc., etc. So once I have this formula for measures rho that are living on a discrete set by projective limit arguments, I can then end up getting this complete general theorem, because this object has nice monotonicity properties as I play with making rho finer and finer and finer. So again, there's some work to be done, but it's the finite support calculation that really gives you this thing immediately. Yeah, it's completely, as long as it's finite, it's good. Of course, in that case, this will become a sum. It will become a sum over I is from 1, S is from 1 to R of nu of S log nu of S of rho of S, but then afterward R is not relevant, and then you can pass to limits and get it for an arbitrary rho that is a nice, in fact, a completely general probability distribution on R. You don't need to assume anything about rho other than that this thing would just exist. Okay. Okay, so these are two very celebrated theorems in a very simple setting. We have i.i.d. random variables, and there have been lots of results when your random variables are not i.i.d. If they have some nice mixing property, then these kind of calculations do not work out so well anymore, because this, when I wrote down this multinomial distribution, that was only true for independence. But you can play, and in fact, you can get more general theorems out of the Gartner-Ellis theorem, because for Gartner-Ellis theorem, you would look at the moment generating function of this kind of object, and that is also perfectly okay. So these are two very simple examples, and there are lots of things that you can do with it in a more general setting. Now, the last thing I want to discuss, so I'll need another 10 minutes, and then we'll stop for today, is that I want to, I've been talking now about the empirical average, which sums up the random variables and takes their mean. I've been talking about the empirical distribution, which records the values of all the random variables and sees that will be converging to a probability distribution on the real line. And now I actually want to go to something that is an even higher version of this, namely, which is called the empirical process. And the empirical process is the following. It basically writes down the entire sample, keeps track of it, except that it doesn't tell you where the sample begins. So what you do, you take the sample x1 up to xn and you periodize it. So you keep on repeating it infinitely often. You do that in order to obtain on the right-hand side an infinite sequence of random variables. The statement that I will be saying is something about infinite sequences, but in fact this is just the repetition of a finite sequence n. And then you define a shift, a left shift on such sequences. And left shift is simply that you say forget the first symbol and only start to read this infinite sequence from the second symbol onwards. And so this is a shift as we see it, for instance, in ergodic theory. And so on the space of all infinite sequences r to the power the integers, I can define a left shift, which simply chops off the first symbol and looks and shoves everything to the left. And I'm going to take this sample, periodize it, and then I'm going to periodically extend it, and then I'm going to shift it exactly n times so that I've seen at the beginning of my sequence all the variables x1 up to xn. And that is what I call an empirical process. So it sees this sequence, except that in the first part it starts with a random index, 1 up to n, each with probability 1 over n. And the rest is just a repetition. So what I'm doing, I'm basically putting my random variables x1 up to xn on a ring, and making them, by putting them on a ring, I make it sort of periodic, and what this thing does, it sort of randomizes the origin of this ring. So if I know this object, I know the entire sample, except I don't know where the sample begins, because I think of the sample as having put it on the ring. But otherwise it contains all the information. It contains the information of the order in which the random variables appeared. Now, this is a random variable that lives in a space. This is a probability distribution in the space of all infinite sequences. And it is also automatically shift invariant, because I have made it shift invariant by putting it on a ring and randomizing the origin of the ring. So this is not only a probability distribution in the probability measures on the sequences, it's in fact an element in the shift invariant sequences, and I put a theta star here to remind you that this means those probability distributions that are shift invariant. Maybe next time I should put a theta up here to remind you that it's invariant under this left shift. But the left shift is a very standard thing. Okay, so this is a subset of all the probability measures. So this is a very rich object. It tells you the entire sample up to where the sample begins. And here's a theorem. It's Sanov's theorem at the process level, and I believe that the very first person who wrote, the people who wrote this down were Donsker and Varadan. And they say this sequence of random processes, suppose now that μn denotes the probability measure for this random process. This satisfies an LDP on this big space of theta invariant probability distributions on infinite sequences with rate 1 over n and a certain rate function, where q is any element in this big set. And the rate function is sort of a limit of the rate function as we saw it in Sanov's theorem. It says take the projection of this q onto the first n coordinate. So q is a probability measure on infinite sequences. Only look at the first n symbols. Then you get a projected law on the first n symbols. Take the relative entropy of that projected law with respect to the law where the first n symbols each have probability rho, which is rho to the n. Divide by n and pass to the limit. You get a limit which we call the relative entropy of q with respect to the infinite sequence probability distribution rho to the power n per symbol. So that's why we call it the specific relative entropy. You take the relative entropy over n symbols, divide by n, pass to a limit. And that limit is what appears as the rate function in the empirical process, large deviation theory, and it is a relative entropy per symbol. This limit exists because you can prove that this quotient is decreasing in n. And so this is for every fixed q, this is a decreasing sequence, and therefore it has a limit. This limit might be 0, it might be infinity, but it always exists. And if you give me just any complicated measure on in this set, this is not an easy thing to compute, but it certainly exists. And this quantity is actually this is actually related to something that in ergodic theory is called Kolmogorov-Sinai entropy. So there is again a deep link here with what we see in information theory and ergodic theory. And this object here, which exists but is not easy to compute in general, unless Q would be a very nice measure, but if Q is a complicated measure, then you may have a hard time computing this, but the object exists, and it is linked to what people in ergodic theory call the Kolmogorov-Sinai entropy, which is a way of quantifying the complexity of a process of a random process. So if you give me a random process consisting of random variables taking values in R, then you could say, is this process very random or is it not so random? And there is a notion of complexity, of how random it is or how not random it is. And this notion also pops up in this quantity here. It would require me somewhat of a discussion to go deeper into that story, but again, here the theory touches with information theory and ergodic theory, and there's some very interesting things that one can say.
In the previous slide, your x1, x2, xn are i.i.d. rows.
Yeah. Well, that's here too. So I start with a process. This is still for the i.i.d. rows, and that's why the measure with respect you do this is the row still to the power n. Okay, so I'm using that. If you would start with a process that would not be i.i.d., you would get the same result, but this would have to be replaced by the law with which you start. And then this law has to be relatively nice, because if that law would already be very messy, I would have some problems actually getting this theorem. But that's also the case for Sanov and Cramer. If you can do it for non-i.i.d. sequences, but they have to be halfway decent in order to get a nice LDP. So I'm giving you the story here only for independent random variables, but here you could replace this by something much more general, and it just would mean that this thing here would change. Okay, I'm getting close to the end. So we've been talking about three rate functions. A rate function for the empirical mean, where x is running over the real numbers. A rate function for the empirical distribution, where nu is running over the probability measures on R. And a rate function for the empirical process, where Q is running over all shift invariant probability distributions on infinite sequences. And these three rate functions we have computed for the case where the random variables are i.i.d. And we have found that these rate functions are always convex. In fact, these two rate functions here are even strictly convex. And this rate function here is not strictly convex, it's affine. Because this is an infinite dimensional object. The space Q is an infinite dimensional space, and so the convexity becomes affineness. And as I said, there's a deep connection with information theory, which I am not going into, but it's certainly where you see that large deviation theory meets the system, meets dynamical systems, for instance. Very, very interesting. And again, let me emphasize that if I would not have i.i.d. random variables, but I would have a nice sequence that has some nice mixing properties, for instance, Markov processes or Gaussian processes, I can redo all of this. And for these processes also, the large deviation principles have been proved, the rate functions have been identified. The rate functions for these two are always something that is relative entropy-like. For this thing, you get some other formulas. And in fact, this is the richest rate of large deviation principle, and you can apply the contraction principle to get this one, and you can apply the contraction principle to get that one. So in a way, this is the most general thing that you got out of this projective limit argument, and all the previous ones after you have done this would follow from the big one by the contraction principle. So everything hangs together. You can go forward, you can go upward in richness and come down in richness as you want. It's a whole structure. So let me end this afternoon by giving you a number of references. Varadan started the theory in the 60s when he was actually not looking at large deviation per se. He was interested in stochastic, well, in diffusion equations and large deviations of diffusions, and he built up a formalism and then gradually realized that this formalism was extremely powerful. And then I think it's to the credit of Richard Ellis that he sort of pushed very much this link between large deviation theory and statistical physics. He was working on it before. Oscar Lanford realized this before. He also has written a big overview paper on this, and people realized, and as they had realized already a bit before, but it became gradually clear as Varadan worked on this more and more, that there was a deep link between statistical physics and large deviation theory. There is a somewhat more abstract book, very beautiful, by Dorschel and Struck, that sort of puts this theory into a more general perspective and also goes into Gaussian processes, by the way, and brings in geometric aspects. Then there is a book that is, I guess, the most cited book by now in large deviations by Dembo and Zaitouni. It contains a lot of information, but it's sort of hard to read. Varadan's book is lovely to read because it's not too big and it exposes it very well. Ellis's book is also nice to read, but it's very big. And it tries to do many things together. These books are also quite difficult to read, but this is certainly, I would say, the most complete book. I wrote a much simpler book in which I sort of outlined the very basic principles and then showed how you could apply this to some nice questions involving, statistical hypothesis testing, parabolic Anderson model, polymer chain. So I wanted to show that. And since then there has been a whole range of books that have been very valuable. Most recently there was a book by Timo Sepolin and Rasoul Aga, and there was a nice book by Rafael Cerf. And so there continues to be books exposing the theory, and so by now this is a very big area. So Ellis and Dupuy wrote a book where you can approach large deviations from the point of view of optimization. So there are various different viewpoints, and there are interesting books that talk about large deviations from a particular aspect in a particular area. You will even find books that talk about the role of large deviations in chemistry, and so I stopped here, and that's not because I stopped thinking after 2000. I'm still here and using it very frequently, but there's a long list, but I somehow think it all started with this book, and this book by Dembo Zaitouni is really to be highly recommended because it's very complete and very nice, and it's become a kind of standard reference work. Okay, so tomorrow, part 2, where I zoom in on one particular application that has some nice features. So thank you very much. Yeah, this convexity, so in principle, a rate function need not be convex in general, because you could say, give me a rate function on a line, maybe I dilate the space a little bit, And by dilating it, something that was convex could become non-convex or the other way around. So a priori, there's no reason why a rate function should be convex. However, if you are in a nice, so you have to be in a vector space to be able to talk about convexity, then it very often happens that it is convex. But very often this is linked to a situation where the random variables that you look at are not very strongly correlated. Somehow the feeling is, and I cannot make this very precise now, but if you are dealing with random variables for which the dependence is not very strong, you seem to very often end up with convex rate functions. You can have rate functions that have more than one zero, so they could touch two zeros. You could have rate functions that hit zero, stay zero for a while, and then come up. When I was talking about the charged polymers, we saw examples of that. But this non-convexity, either that you lose the strict convexity or that you become really not convex at all, come from very strong dependencies. And there are lots of examples now where you put something in some kind of random potential, and the random potential causes that everything has a very strong dependence, or like in this charged polymer that you say whatever happens here on the polymer depends very much on what's happening there, because they could meet these pieces and have some interaction with each other. So my answer to your question would be weak or moderate interactions will always give you convex rate functions, very often strict convex. Strong interactions, you may lose it. And the strict convexity is nice because it would mean that if you want to look for minima of this thing with respect to linear functions, you have unique minima. And with non-convexity, you get non-unique minima. And sometimes this is very interesting because it will signal something interesting happening. Okay, so a lot is possible. I'm not sure if I've answered your question, yes. But in my head, convex is interaction is moderate.
But in your last case as well, when you constructed this whole thing,
yeah, but then it's
have i.i.d sequence, but you still
yeah. So if I take so this thing is still convex. It's not strictly convex, but it's affine. And if I would replace this by a dependent sequence, then as long as this is not too wild, then this thing is true and I get the defineness for free. But if I start to have things with a big interaction, I may have to be worried that this thing is no longer true. And then there could be some other rate function that does not have this simple representation anymore, and it loses, it may lose its convexity.
Something about optimization you mentioned, the connection?
Yeah, so this comes from the fact that in the end, many rate functions are given by some kind of variational principle. So I gave you simple examples where the rate functions are computable explicitly. Well, this specific relative entropy was already a bit more complicated, but sometimes you can compute this and sometimes you cannot. If I start to look at sequences with dependencies, what I basically do is I say if this is built from an i.i.d sequence plus some biasing, I can use Varadan's lemma, and then I will get a rate function that is given by a variational principle. So the fact that variational principles appear here means that you have to optimize something, and therefore that optimization problems actually appear in your description of your rate function. And this is an idea that Ellis and Dupuy have sort of capitalized on by saying they derive LDPs in a more general setting, and they use variational principles to describe them. And these variational principles can be things of the type you have to optimize over all possible trajectories that have a fixed beginning point and a fixed end point, and then your rate function will in some way pop out of an optimization problem. And you can actually place large deviation theory in a whole perspective of optimization theory, and that's what they have. They wrote a whole book about that. But it's not giving you so many new results. It's placing the results in a different context, and this is very interesting to do. If I would do that, I would, you start to see the theory also from a different angle, and that's very interesting. But okay, does that answer your question? Yeah. Okay. Yes.
So let's say I have two family of probability measures in R. Then suppose I take the convolutions.
Yeah.
If the original one satisfies LDP, will the convolution, the new family will satisfy LDP?
Oh. I guess it should be, because convolution is making the independent sum of two random variables. So if I would start with having two independent sequences and I would make the convolutions, it would be okay. I would get as a new rate function something that I get by taking the convolution. So then also the moment generating function would factorize. So indeed, you would be able to do that. If you get dependencies, it's probably still okay, but I would have to think for a second about what your rate function would be. I guess then it should be running through Gartner-Ellis theorem, because Gartner-Ellis theorem with convolution you get your hands on the moment generating function. So probably it's something like you take the Legendre transform and you just sum the two phis. You have a phi 1 and a phi 2, and you sum them and subtract that from the inner product, and you get it like that. So it should be something like that. But I'd have to sit down for a second to say how does it exactly work out. But you can easily try for yourself.
So you said something about the central limit theorem from the
Yeah.
Deviation. Now, is this would this be a reasonable? I mean, you'll need probably more in order to have the LDP first. But does this give some sort of a better insight, or is this a better way to approach?
So if you have an LDP, and the LDP has a unique zero, which is very often the case, you have a law of large numbers. That's trivial because the probability that you're outside any small neighborhood will be exponentially small, Borel-Cantelli, and you get it. Very often this rate function is parabolic near its minimum. And then the curvature here should be 1 over the variance in the appropriate CLT. You would then sort of think, what you're thinking of is that you are pretending that you can apply this principle here in a neighborhood where x is m plus something small, and then if this thing is quadratic, then this will become the square of that something small, and you would see a Gaussian appearing here, and then you would say, well, if I could pretend that my large deviation theory would be true uniformly, even in a small sphere here, and here you have a region that is shrinking, whereas we were talking about a fixed open set or a fixed closed set. So if you do that, you can more or less guess what your CLT should be. Unfortunately, there is no theorem that will guarantee that if you have this situation that a CLT is always true. You need a little bit more. You need some kind of regularity. And Bryc proved a theorem in which he said if you have an LDP and you also have some kind of analyticity in a small strip around the real numbers, then you're okay. But that last thing is typically very hard to check. And so in practice, what happens if you want to prove a CLT, you might guess it from this, but then you're up in the air and you have to do it anyway. And what you do, you get your martingale central limit theorems off the shelf and you start to do it again all by yourself. I have almost no examples where the LDP plus a little bit of work would give you the CLT. Mostly you just have to start from scratch and do it. But it's a good way to sort of guess. If you know this, then you can already say, I can guess what the variance is, and then maybe when you see that, you get some extra idea about what to do when you want to prove the CLT. But there's no easy link, unfortunately. There is a link, but it's complicated.
So physicists seem to assume that
Yeah.
this.
Yeah, and I would guess that out of 1,000 cases, 999, it's okay. And then they would say, well, the 1,000th one, well, yeah, you shouldn't have looked at it. But for mathematicians, it is an issue.
Okay, thanks.
Okay, thank you very much.